All right, let's get right into it. We're always hearing about these amazing scientific discoveries that come out of super controlled lab experiments. But what about the really big, messy, real world questions? Things like how parenting styles affect kids, or the impact of economic policies, or even long term health habits. You can't just stick people in a lab for 30 years to figure that stuff out. So, how in the world do scientists get answers? And that, right there, is the big question we're tackling today. When that perfect, sterile, controlled experiment just isn't an option, researchers have to pull out a whole different toolkit to make sense of the world. So let's go ahead and open up that toolkit and see what's inside. You see, in science, the absolute gold standard for figuring out cause and effect is what's called a true experiment. But so often, for really practical or even ethical reasons, that gold standard is completely off the table. I mean, think about it. You can't ethically assign one group of people to start smoking just to see if it causes cancer, right? Of course not. And that is the experimenter's dilemma. So what is the actual difference here? Well, think of it like this. In a true experiment, the researcher is like a movie director. They create the entire scene, they control the conditions, and they randomly assign actors to their roles. But in a quasi-experiment, the researcher is more like a detective. They show up to a scene that has already happened, and they have to carefully piece together what went down based on the evidence that's already there.
Let's make this super concrete. Imagine we want to study if ibuprofen helps prevent Alzheimer's. In a perfect world, the experiment, you'd randomly tell one group to take ibuprofen for 20 years and another group to take a sugar pill. But a much more realistic approach, the quasi-experiment, is to simply find a group of people who already take ibuprofen regularly and compare their Alzheimer's rates to a similar group of people who don't. You're studying their pre-existing choices.
So, since you can't always play the director, you have to become that investigator. And every good investigator needs their toolkit. For studying life as is, two of the most critical tools in that kit are quasi-experiments and correlational designs. Okay, tool number one, the quasi-experiment. The name itself, which comes from the Latin for seeming like, tells you pretty much everything you need to know. It looks like an experiment, it feels kinda like an experiment, you might have groups you're comparing, but it's missing that one magic ingredient. The researcher doesn't have control over who gets what treatment. And tool number two is the correlational design. This one is all about observation and measurement. You're not really creating groups to compare. Instead, you're just looking at two or more things out in the world. Let's say how many hours of sleep a person gets and their scores on a test. And you're trying to see if they move together. Is there a pattern? Now, finding a pattern is one thing, but actually understanding what it means is a whole other ballgame. So how do researchers take these patterns they find and decode them to figure out what's really going on? Well, when scientists look at a correlation, they're basically checking for four key things. First, is it linear? Can you roughly draw a straight line through the data points? Second, what's the sign? Do the two things increase together? That's positive. Or does one go up while the other goes down? That's negative. Third, what's its magnitude? Just how strong is this relationship? And finally, they ask, what's the probability that this whole pattern is just a random fluke? Okay, so this might look like a bunch of scientific gobbledygook, but it actually tells a complete story. That R just stands for the correlation. The plus 70 tells us it's a pretty strong positive relationship, and that p-value of 0.001, that means the chance of this pattern being a total coincidence is only 1 in 1,000. In other words, this is a pattern we should definitely pay attention to. But what does a correlation of, say, 0.7 really mean in the real world? Well, there's a neat trick. If you square the correlation number, you get something called the coefficient of determination. It basically tells you how much of the change in one thing can be explained by the other. For instance, a famous study found that the firmness of a person's handshake could explain about 31% of how positive their first impression was. So if you look at it this way, a firm handshake isn't the only thing that matters, but it's not nothing either. It accounts for almost a third of that first impression. And the other 69%? Well, that's everything else. Your smile, your clothes, what you actually say. Correlations help us start to figure out how much each piece of the puzzle really matters. Okay, we've established that correlations can be really powerful tools. But this brings us to what is, without a doubt, the single most important warning in all of science. Seriously, once you get this concept, it'll change the way you read news headlines forever. Here it is, the big one. Say it with me.
Correlation does not equal causation. Just because two things are related, just because they move together, does not ever automatically mean that one of them causes the other. This is the whole shebang right here.
So why not? Well, it all comes back to where we started this conversation. Remember how a true experiment requires the researcher to create and control the situation? Correlational studies don't do that. They're just observing the world as it unfolds naturally. And without that control, you can never, ever be 100% sure what's causing what. Specifically, there are three major logical traps we can fall into. The first is the causal direction problem. Did A cause B, or did B cause A? We don't know. Second, you have bidirectional causation, where maybe they're both causing each other in some kind of feedback loop. And then there's the big one, the third variable problem. What if there's some hidden factor C that's secretly causing both A and B to happen? Let's use the classic example. We know there's a strong correlation between insomnia and depression. So, causal direction. Does not sleeping cause you to become depressed? Or does being depressed cause you to not sleep? Both sound plausible, right? Bidirectional. Maybe it's a vicious cycle where lack of sleep makes depression worse, which then makes your sleep even worse. And the third variable. What if something else entirely, like major stress at work, is causing both the depression and the insomnia? See, the correlation alone can't tell us which of these stories is the right one. So if correlation isn't causation, does that mean these studies are useless? No, absolutely not. Remember, researchers are detectives. A correlation is just the first major clue. From there, they use some really advanced techniques to build a much stronger case and get closer and closer to the why. They have some pretty sophisticated tools to dig deeper. For instance, they can use statistics to test for and control for a suspected third variable, just to see if the original relationship is still there without it. They can also build complex models to test which theory, A causes B or B causes A, actually fits the data they've gathered over time. It's all about systematically ruling out those other explanations. And this brings us right to the final critical question. After all of these warnings, after hearing that correlation can't prove causation, why do we even bother with them? What's the point? The point is just about everything else. These studies are absolutely essential. They allow us to make incredibly powerful predictions. They let us investigate massive, important questions that we could never, ever ethically or practically test in a lab. And maybe most importantly, they act as the detective's map. They don't solve the case on their own, but they highlight all the hotspots, and they tell us exactly where we need to look to find those final, definitive clues.